Hello and welcome back to Calculus. First, I'd like to thank all the nice people that support this channel by liking and subscribing. Today, I'd like to continue with methods of integration, specifically integration by parts. However, before we get to the formula, how to use it, the technicals, and the examples, I'd like to begin with an investigation and visualization of what this is going to be about. We first begin with this complicated looking graph. Basically what we have is the x-axis and the y-axis, only instead of x we have v's and instead of y we have u. Now the function, which is the blue line, is technically going to be f of v. And now we have two different lines, their variables and their values, and of course we have area 2 and area 1. And basically what we're aiming to find is area 1. However, what we're going to find in the end is going to be an expression in terms of unknowns and variables, because we do not have any specific numbers here. So in order to guide us, let's first take a look at a few questions that we have to answer in order to find an expression for area of 1. Now, the first question I'd like for you to answer is, how would you represent area 1 with integrals? As you know, bounded integrals, or in other terms, definite integrals, are used to find areas under the curves. So in this case, we have the area from v1 to v2 of the function f of v. So that means if we were to express this area as an integral, we would begin with the integral from v1 to v2, because this here are the bounds, of the function of the blue function. So in our case, that would be f of v. And of course, in the end, we have to add dv. This was quite simple, so let's move on to the next question. Now, question 2 says, if the axes are interchanged, so now the x-axis is going to be u. Let's just try to imagine this. Now here is going to be u, and the y-axis is going to be v. This is also why I wrote v of u, because now the function technically is not going to be f of v anymore, but f of u. Basically, v and u switched places. How would we represent the area with integrals for area 2? Well, we start with the integral, this time from u2 to u1. However, what is the function going to look like? Now, if you remember functions, there is one thing that describes when x and y variables change places, and that would be the inverse function. So here, what we do is take the inverse function, f to the power of -1. Well, this is not a power technically, it shows inverse, and the variable is going to be u, and we do the integral du. Now they ask, what is the sum of the areas 1 and 2? Well, that's not hard. All you have to do is take integral area 1 and add the integral for area 2. Okay, so now that these first 3 questions have been answered, let's move further to the next 3 questions. Now, the next 2 questions are quite easy. It says, express the area of OFBD. So in this case, the area would be this one, this big rectangle right here. Now that we know the corresponding x and y variable, means we know the width and we know the length. So technically, the area of this big rectangle is simply going to be v2 multiplied by u2. And then they asked us to express the area of OEAC. So this is going to be right here, this smaller rectangle. Once again, we have the length and we have the width. So the area can simply be expressed as v1 multiplied by u1. Now lastly, question 6, I put it in a red box because it is the final question and is the most important one that is going to give us what we need. It says express area 1 in terms of OFBD, OEAC, and area 2. So basically what we have to do is that we take this big rectangle right here. Then we have to subtract this part, area 2. And of course, after that, we also have to subtract this smaller rectangle inside. And as you can see, what we have left after is going to be the area 1. So let's go ahead and do that. So we know from question 1 that area 1 can be expressed with this integral. And this is going to be equal to the bigger rectangle, in this case, v2 multiplied by u2. Then we have to subtract the smaller triangle, whose area is v1 times u1. And then we also have to subtract area 2. And we don't have to rewrite this because we already have that expression from question 2. And right here we have the final expression. Now I want you to pay very close attention to how this is written. This is a non-rigorous visualization of the technique integration by parts. The formula actually is going to look extremely similar to what we have here. Now I can tell you further that this technique integration by parts is actually also related to the product rule for differentiation that we learned in part 6. Product rule stated that if we have two functions u and v that are multiplied together, and when we compute the derivative of these multiplied functions with respect to the variable x, what we're going to get is the original of one function multiplied by the derivative of the other, and plus the other way around, the original of the first function multiplied with the derivative of the second function. If you do not remember, please go back to part 6. Now, next, we can actually integrate this identity from both sides, since this is an equation. This is actually going to simplify, because on the left-hand side, we're doing the derivative and then the integral. So that basically equates to doing nothing. So what's going to happen? U times v is going to stay. And the other two integrals I cannot compute, so I will just write them down as they are. And then next, I'm going to do some rearranging. Specifically, I'm going to move one of these integrals to the other side. And finally, the answer is going to be integral of u times derivative of v is equal to the two original functions u and v multiplied together minus the integral of original v times the derivative of u. And this right here, ladies and gentlemen, is the rule for integration by parts, more specifically the formula. I can actually write it down a bit simpler, perhaps in a more understandable language. What happens here is that when we compute an integral where two functions are multiplied together, we automatically assume that one of them is the original u and the other one is the derivative of v. And once we do this integral with respect to the variable x, what we're going to get is original u times original v minus the integral of v times the derivative of the u function. Of course, yes, as you see, our answer will still contain another integral. However, most of the time it's going to be simpler to compute. Integration by parts allows you to convert an integral of the product of two functions into another integral, which is most of the time easier to compute. Typically, I can tell you that integration by parts is used to integrate logarithmic functions and inverse trigonometric functions. It's also extremely useful for product of two functions, for example, the following ones. These are a few examples: x ln x, x cosine x, e to the power of x cosine x arcsine x times ex, and so many more. So let's pick two of these and solve them as examples. Let's just say that for the example, we do the integral of x times e to the power of x. And here we have two functions multiplied together, meaning that we have to use integration by parts. Now, please remember that we assume automatically that the integral we have, one of the functions is going to be the original u, and the other function is going to be the derivative of e. In our case, u is equal to x, so v prime is going to be equal to e to the power of x. Now, the next two pieces of information that we're going to need is, first is u prime. Now, u prime is the derivative of x, which is simply 1. And of course, we also need the original v. Now, if we have the derivative of v, means we have to do the integral of the derivative in order to find the original. However, lucky enough for us, here we have the exponential function e to the power of x, where neither the integral or the derivative can change how it looks. So here, v prime was e to the power of x. Original v is also going to be e to the power of x. Now, we use our rule for integration by parts and we construct the following. We know that this integral is original u times original v. So horizontally here, these two things are going to multiply. What we get is x times e to the power of x. And this we're going to subtract by original of v, which is e to the power of x, times the derivative of u, which is simply 1, and I can just not write it. Now, as you can see, this integral has become easier to solve, because when we do integral of this part right here, we know that the answer we're going to get is simply ex plus c. So that means the final answer is going to be x times e to the power of x minus e to the power of x, and of course plus c at the end, since we're solving indefinite integrals. Alright, this seemed simple enough, so let's take a look at another example where we have to integrate x times ln of x. If you want, try to pause the video and solve it yourself first. Once again, we immediately assume that the integral we have contains of the original u, which in this case once again is going to be x, and the v prime, the derivative. In this case, this is going to be ln of x. However, you might immediately realize that here we will hit a roadblock, because even though we can find u prime, which is equal to 1, we are unable to find v, because we do not know what the integral of ln x is going to be. So that means we have to switch it up, meaning this time u is going to be ln of x and x is going to be our v prime. So then, in this case, u prime, the derivative of the natural log of x, we know is 1 over x. And of course, the original v is going to be x squared over 2. Once again, the original integral is going to be equal to original u times original of v. So we write ln of x multiplied by x squared over 2 and subtract the integral of original v and u prime. So in this case, these two things multiply together. So this would be 1 over x multiplied by x squared divided by 2 dx. Now you can probably see in the second integral, some things will simplify. For example, x on the bottom together with the squared. So basically here, simplified, what you're going to have is going to be the integral of x over 2 dx. Now this integral here, we can simply solve with the power rule, and what you're going to get is x squared divided by 4 plus c, meaning the final answer to this integral will be the following. It will be ln x multiplied by x squared over 2 and minus x squared over 4 plus c. And here would be your answer. From this exercise, you might have noticed that picking u and v prime in your integral can sometimes be a little bit tricky. And here I can only give you 2 tips. In cases where you need to integrate the product of a polynomial function with the exponential function, in this case, the first example, x times e to the power of x, you should always differentiate the polynomial. Well, x to the power of 1 technically is still a polynomial, but if you have a more complex one, you would still set u as your polynomial since its derivative is easier to compute. And the second reason is that the derivative or the integral of e to the power of x never changes, so it will make your life much easier. Now, in other cases, for example, in our second integral, where you need to integrate the product of a polynomial function with the logarithmic function, so in our case x times ln x, you should always differentiate the logarithmic function, meaning you set u as your logarithmic function and then you find u prime. Because at the end of the day, we are able to do the integral of the polynomial to find the original v. However, we are unable to find the integral of a logarithmic function. So these are the only 2 tips that I can give you in order to pick u and v prime more effectively. Other times, if you do pick them wrong, you will realize later on when you solve that it's unsolvable. And immediately you will realize that it's probably you picked the wrong u and v prime. Now, continuing this integral, before we set our v prime as ln x and we had to do the integral of ln x, and at that point I said that we cannot find it. However, I may have over-exaggerated a little bit, because now I'm going to show you exactly how to find the integral of just the function ln x dx. You can actually solve this by using integration by parts. But you might ask, how does this work? It's just ln x. There's no multiplied by the second function. And so this here would require a little bit of brainstorming, because technically ln x is multiplied by 1. So that means the other function that you have is simply 1. This means when applying integration by parts, now we can set our u as ln of x, and then we can set our v prime as just 1. So that means that u prime, derivative of the natural log of x, is going to be 1 over x, and of course the original v is just going to be x, since its derivative is simply 1. So now we apply the integration by parts rule. We first multiply the 2 original u and v together. In this case, that would be ln x multiplied by x, and then minus the integral of v original times u prime. So in our case, x times 1 over x dx. Immediately, you can already see x times 1 over x just simplifies to 1. And the value of the integral of 1 is simply going to be x. So the answer that you're going to get here is going to be the following. It's going to be ln x times x and minus x plus c. And here you have found the expression for the integral of ln x. Now, I did also mention in the beginning that you can use integration by parts in order to find the integrals of inverse trigonometric functions. So now this is exactly what I'm going to show you. We're going to try to find the integral of the arc cosine of x dx using integration by parts. And immediately the first step we're going to do is going to be the same as integrating ln x. This right here, what we have is simply the integral of the arc cosine times 1. So now that means we can set our u as the arc cosine of x, and the v prime we're going to have is 1. Now immediately the original v is going to be x, you already know that, but what is going to be u prime? Now please recall from part 12 where we spoke about implicit differentiation, I also showed you the derivatives of the inverse trigonometric functions. If you do remember, you will know that the derivative of the arc cosine is going to be 1 divided by the square root of 1 minus x squared, and this whole thing is negative. So now, with the help of integration by parts, we can rewrite the integral of arc cosine as x times the arc cosine of x minus the integral of original vx multiplied by u prime. Now please note that u prime carries a minus, and integration by parts also carries a minus. So two minuses is going to combine into a plus. And on the bottom of the fraction, we're going to have 1 minus x squared. Now, this integral that I changed into the red color here can be solved using integration by substitution, which we talked about in part 18. So I will not show the step-by-step solution and simply tell you that what you're going to get for this integral is negative square root of 1 minus x squared plus c. So that means the final answer for the integral of the arc cosine function is going to be x times arc cosine of x minus the square root of 1 minus x squared and plus c. And this right here, ladies and gentlemen, is the answer to our integral. Now, all of this may seem extremely complicated. However, it's not as much hard as you think. The only thing that you do have to do right is to pick the correct u and v prime variables in order to make your life easier. In the next video, I will speak about integration by parts when we have a definite integral, and something called a cyclic integration by parts, which is a continuation of solving integrals of this kind. So I really hope to see you there, and have a nice day. Bye.